Well, hello, pre-calculus class. So here we are doing a week of distance learning, and I hope these videos will be helpful to you guys. The one nice thing about them is you can replay them, so if there's something that I explained that needs to be explained again, you can listen to it again, and hopefully it becomes more clear. And if not, you can obviously reach out to me, and we can work out a Zoom meeting or something else if you guys need that. But I just don't want to lose the whole week here, so you've been doing very well. We're moving along. And so we're going to try to finish up chapter 5 together this week. So we've got 2 sections to do, and then you'll have some review problems. And the plan was to originally have taken the test on Friday. We will probably postpone it a couple days, just so that way we get back on the following Monday after this week, and then take the test maybe on Tuesday of next week. After we've gotten a little bit of review together. So that'll be the plan, but by all means, reach out to me if there's something you don't understand in what we're going to be going through here today. So we're going to be looking at the law of sines, first of all, in 5.6. Okay, in order to get started here, I just want to talk a little bit about what it is that we're after here. We've been talking about several different theorems together and identities, and you've been writing those down on kind of a sheet of them that you're keeping with you, so you can even use that on the test that's coming up. And so we've solved right triangles like these, and with right triangles like these, you can make use of things like the Pythagorean theorem, right? We could figure out what this side right here is by just doing, a squared plus b squared equals c squared, and we could solve in this case, let's say for the b squared here to know what this side is through that. We also have learned through our trigonomic identities that you're able to make use of sine, cosine, and tangent as long as the triangle is a right triangle, like this one over here, where if we have a degree measurement and we have one side length, we can use tangent, for example, to get this length. We could use sine of this angle. Remember, it's always opposite over hypotenuse in order to get this length. So we could use those theorems to go about solving these. We also know the sum of the angle measures 180 degrees, so we can always add this 38 to 90 degrees here, and we could then subtract that from 180 to get our missing angle. So these are all things that we've already learned together. Well, the law of sines is useful whenever we have a triangle where we don't have necessarily a right triangle. So this is in cases where we have a triangle ABC with different lengths of those sides, and they have opposite angles, capital A, capital B, capital C. And what we learn from the law of sines is the ratio of an angle, in this case the sine of an angle, and the opposite side of that angle equals the ratio of the sine of another angle in that triangle with its opposite side, or another angle in that triangle and its opposite side. So let's get some, I want to do a little bit of derivation so you see how they came up with the law of sines. So imagine that we have a triangle here, ABC, and what we've done is we've drawn a height here on the triangle and shown it with a dotted line here. So once we've done that, we've kind of divided this acute triangle into 2 right triangles, right? We now have a triangle that comes this direction, and then we have the little triangle over here, as well as then the full triangle that we started with. But notice if we look at this angle A and we look at the sine of A, which would be opposite over hypotenuse, the opposite to angle A here could be this H, and then over C, which is the hypotenuse. If we're looking here from angle C, we can do the same thing and do a sine of that, and we'd get H over A. Well, we could rewrite both of those and just multiply this C up to the A. We could also multiply this A up to this side on the sine C, and we get both of these to be equal to H. Well, if they're both equal to H, then we can set them equal to one another. Since they both equal H, then we can just say that this guy equals this one. So C sine A equals A sine C. And then we can just rewrite that as C over sine C equals A over sine A. And this is what we know as the law of sines. So this is just a quick derivation of that law. But all you're really going to have to do in the problems ahead is make use of the law of sines together. So this is kind of a quick review of how they actually went about deriving that law. So it looks like this: A over sine A equals B over sine B equals C over sine C. Note that you can also flip these ratios and have sine A over A, sine B over B, sine C over C. Okay, so I'm now going to test a little bit of your geometry memory. Here we've got a couple of triangles, and in this case, you see that we have an angle, and then we have an angle, and then we have a side. This is also known as, you probably remember these, angle, angle, an angle, angle, side, a triangle. Here we have an angle, then a side, and then an angle, also known as an angle, side, angle, ASA. So in these cases, we can use the law of sines to get the rest of the triangle. Note that in both these cases, we have two angles, and that angle, then the other angle that we don't know, can be derived from just subtracting the other angles from 180, and same thing for this angle over here. And then we can just use that ratio of the sine of an angle, or the length of a side over the sine of an angle, and then we could use this length, this was saying being x in the first case, over the sine of this angle. And we could derive, then get an answer for the sides that we don't know. Similarly, we can do the same thing on this triangle over here. So let's look at example 1 on page 269 and just walk through this together. Notice it says solve triangle ABC if angle of A is 34 degrees, angle of B is 76, and the length of A is 9 centimeters. It then says here round the lengths to the nearest tenth. A couple of things I want you to remember. Number one, whenever you're doing these triangles, make sure that you set your calculator to degree mode. For a lot of the previous work we've already been doing, we've been using them in radian mode for a lot of times. But make sure on these that you do set them for degrees. So that's important for both this lesson and the next lesson that we're going to be looking at. We're going to be looking mostly at triangle measurements with angles given to us in degrees. So make sure you have the mode of your calculator in degrees while you're doing these. Okay, so double check that. The other thing to remember is when it's telling you to round the lengths to the nearest tenth, don't round them until the very end. So try to keep them, if you're doing it in calculator, just keep the long number in the calculator going until you get to the very end, and then you round to the tenths. If you, for some reason, have to write down the number as an intermediate step, I just encourage you to keep several points after the decimal until you get to the very end as much as possible, and then round at the very end. So here we're trying to solve the triangle. So whenever it says solve the triangle, what it's asking for is for you to give the angles that are unknown right now and the sides that are unknown. So at the moment, we don't know the angle measurement of C, nor do we know the side length for little c, nor the side length for little b. This, again, is an angle and a sine. And we can use the law of sines to solve for everything else in this triangle. The first thing we might do is just figure out what the angle C is, because we know the angle C must be 70 degrees. How do I know that? Because we just subtracted, again, within a triangle, all three angles have to equal 180 degrees. So we just subtract 76 and 34 from 180, and we get 70 degrees for angle C. Then for the other ones, we just set up our law of sines. In this case, B, an unknown, over sine B equals A, which in this case is going to be our 9, over sine of A. So notice that we want to make sure we use the side with an angle here, A with this little a. We want to use that one in our proportion because we know both of those numbers. And then for the other one, we've got the other angles. We just plug in this guy and then B for this. And we can solve this for B, right? We can just multiply the sine of 76 degrees up here. And we get B equals 9 times sine of 76 over sine of 34. And again, you get an answer of 15 and some change. Then we can do the same procedure. We do the same procedure now for the other sides. So that was for side B. We can now do it for side C. And again, it's going to be the same proportions that we're setting up, except this time we have the sine of 70 degrees because we're going from this angle, which remember we figured out already was 70. And then we're going to multiply this up, and that will leave us with C by itself, and we'll get an answer of that. So I think you're going to be able to do these problems no problemo. Pun, I guess, unintended, but such a good one, isn't it? Just like being in class. Hopefully you're watching this at 7:30 in the morning, so that way this just brings on all the flavor of what normally happens for us early in the morning, and so that way you get to deal with my ridiculous puns early. Okay, let's look at the next thing. So remember, you probably should remember this from geometry, but the longest side of a triangle is opposite the largest angle of the triangle. This makes sense, right? So if I was just to draw a triangle of any length, notice that whatever angle is the longest one, straight across from it is going to be the longest side. If I draw the triangle like this, again, notice this is the biggest angle, here is the longest side. So always the largest side is going to be across from the longest angle, and then obviously then it is also true that the shortest side will be opposite the shortest angle. This is a good rule of thumb to keep in mind in case you get to any problems and you want to just check for reasonableness of the answers that you're giving. You can check them by this methodology. All right, so again, in the problem that we just did together, notice that here's our angle 34 degrees. These other ones are 76 and 70. Note that opposite 34 degrees is a side of 9 centimeters. Notice the one opposite the 70 is 15.1. And as we would expect, the one opposite the 76 degrees is 15.6. So again, you can check your answers afterward because this will always be the case within a triangle. Okay, let's look at example 2. Here's a word problem. Johann and Wesley stand 360 feet apart on a level football field to observe the flight of a rocket from opposite sides. If Johann records a 72-degree angle of elevation to the apex of the flight path, and Wesley records an 81-degree angle of elevation, determine the distance from the rocket to each observer and the height of the rocket's flight. So usually what's good to do in all of these word problems is to set up a picture. So let's do that first. So this is kind of what we would have for the drawing of the picture. We've got our two individuals. They're looking up at the apex of the flight of the rocket, and we've got the respective degree measurements which they're looking, and we know that their distance apart from one another is 360 feet. So on the basis of all of this information, we can now solve for the D1 and D2, and after we've solved for those, we can then get at this height as well. So first of all, we know that the angle for angle A up here at the top of the triangle is just, again, 180 degrees minus the other two, which we get to then an answer of 27. Then, using our law of sines, we can say D1, which is opposite this angle over here, has to equal A, which is this angle up here. I'm sorry, the sine of A is the angle over here, being below the length of that side, 360 feet. So we're going to put this 360 feet, or we can first of all solve this equation. Remember, take this sine of W and multiply it up. And so that's what we have here. So we have D1 by itself. That's the one that we're trying to solve for. And so we get 360 feet times the sine of 81 divided by the sine of 27. And if you punch that in the calculator, you get 783 feet. Now we can do the same operation for finding D2. In this case, we're going to do the sine of J, which is the 72 degrees for sine J, and then the A, again, is 360, again, over then the sine of this angle, which we already determined was 27. So again, we plug in all of those numbers into our calculator, and we get an answer of 754 feet. So now all we have to do is we can just take one of these observance lengths. It could have been either side of the triangle that you selected. And notice if we use, we're trying to find the height, which is the line that's perpendicular to the ground, straight up vertically to the point which the rocket went up. And we know that is a right triangle, which is important to us because then we can make use of, again, our sine operation. Remember from our remembered phrase, SOHCAHTOA, sine is opposite over hypotenuse. So in this case, it's going to be the H, which is the opposite of this angle, right? Opposite, over hypotenuse, which is the long leg, so 783. And again, we can just then multiply the 783 this way to get h by itself, which is what we want to do. So h is then going to be 783 times the sine of 72. And when you put that in the calculator, you get 745 feet, which is the answer to the problem. Now, just to give as another example, if you want to go over to page 273 in your book, and you go to exercise 7, you will find this, a triangle ABC, where A equals 52 degrees, and B equals 49 degrees, and C equals 16. You're supposed to solve the triangle. So this might be a good moment for you to just pause the video, just stop it right here, and try to sketch yourself a little triangle on a piece of paper, and try to solve the triangle. Give me the length or the angle measurement of the other angle that you don't have, and then tell me the length of the other two sides. So pause the video right now and see what you get. You can come back to this and we'll check your answer. Okay, so hopefully, if you haven't paused it, you need to actually pause it and work this thing out. But I'm going to assume you've come back after having done that. So now let's look at this together. So we know that C has to be 79 degrees because, again, we would just subtract both of these two from 180 and get 79. And then we just use our law of sines. So you can just take A over, again, its opposite angle, which is going to be the angle A, so sine of 52. And then we put in the things that we know. We know our C is 16, and we just determined that the degree measurement for angle C is 79. And so we set up the equation. Again, we're going to multiply this up to get the A by itself. So A equals about 12.8. Then we do the same thing, setting up for B. B over sine of 49 equals 16 over sine of 79. We're going to multiply, again, this up to this side. So B equals, after you do that operation, 12.3. Okay, hopefully you guys got that one right. Now, remember from geometry that there's a special case. The side-side angle is not a case of congruent triangles. And I just want to show you why that is the case. It can be the case that there are congruent triangles, but they may not be. This is what we call an ambiguous case, because there's a couple of different ways in which the triangle can be set up when you're given a side-side angle situation. So notice the drawing that you have here before us. We have a side length that is congruent to another side length, this guy. We also have an angle that's being kept the same, this angle down here. But note, and then this side length is also the same as this side length. But notice that it can either be coming this way and make an acute triangle, or it could come this direction and make an obtuse triangle. So it could be positioned either way. So this is the case in which a triangle can be made one of two ways. So I'm going to talk a little bit about what happens in these kinds of triangles and how we go about trying to solve them when we have this particular kind of case. We're given two sides and an angle. This is what's called an ambiguous case. The word means uncertain, or it has multiple meanings, or it's indistinct. In this case, there might be multiple solutions to the triangle when you're given two sides and an angle like this. So the first case that you could have, and the book goes through these pretty well for you. If you go to page 271, it works through these various options. But the one option is an obtuse or right-angled triangle. So you can have exactly one triangle if the length of A is greater than the length of B. So we have this angle, and then we have two sides. And so what it's saying here is if A is longer than B, there will be exactly one triangle that fulfills that. Now, if A is shorter than B, and the angle A here is, again, obtuse, so it's more than 90 degrees, if this A is shorter than B, note that it's not long enough to make it all the way down to the other side. Therefore, it doesn't actually ever make an actual triangle. It's no triangle at all. So in the case of an obtuse triangle, if angle A is greater than 90 degrees, then the side length A has to be longer than the side of length B. The length of side B. Sorry, I said that wrong. The length of side B. Now, in the case of an acute angle A, again, we're going to talk here about H being, the height is B sine A, which I'll show you in a moment. But if A is greater than or equal to B, or if A equals H. So if A is greater than or equal to B, then we have two triangles because, again, it can be set up. Remember the example that I just gave you before. It can look like this, or it could look like this kind of shape. So there's two different triangles that might be the case if the height is less than A, but A is less than B. In the case where A equals the height, you get into a triangle that looks like this, where the A, so this is the angle we know, if the A is actually equal to the height, then that is just a right triangle. So this kind of is showing what happens here. So in the case in which A is greater than B in an acute triangle, we just have one triangle. If A equals H, we have just one triangle. It just happens to be the right triangle. Now, if we get to a case in which we have an acute triangle where we can have possibly two triangles, it happens in this case where the length of A, which is this red line, if it is both greater than H, so greater than H, which is the height here, but it's less than B, then it can be set up either this way or this way. So we get two different triangle potentialities there. But if A is less than the height of the triangle here, then it doesn't make a triangle at all. Note that no matter where I swing this leg, it never can get all the way down to this leg. Therefore, it never actually makes a triangle. Now, I just encourage you to go over this chart on 271 and kind of look at it for a while and make sure that it makes sense to you before you move on to the next part of this. Okay, well, let's look at example 3, and this is asking us to determine the number of possible triangles in each case. So let's consider, for part A here, triangle JKL. If J is 3.5, K is 5, and J is 97 degrees. So notice here, if J is 97 degrees, that means that this is an obtuse angle, right? So in the case of an obtuse angle, again, if J, which is the side opposite the angle J, if this number is smaller than the K number, which it is here, note what happens. The K side is 5, so it gets way up here. But then 3.5 isn't long enough to come all the way back down and actually touch this line. So we know instantly if this number, this J, is smaller than the K, it's no triangle at all. So in this case, it's no triangle because this is an obtuse angle. We could also prove this to be the case if you went ahead and tried to put this into the law of sines. See what happens here. When we put in these numbers, we would get that the sine of K equals 5 sine 97 degrees over 3.5. Or when we get all that, the sine of K has to equal roughly 1.4. Well, this at this point should give you a warning, because remember, sine values can only range from -1 to 1, and this is larger than 1. As a matter of fact, you put this in the calculator, you'll get an error. So you know here that there's no triangle. Okay, what about for case B? What about triangle XYZ if x equals 4, z equals 5, and again, the angle measurement of z is 55. So in this case, we have an acute angle, right? And so here's a good drawing of that. We have z equaling 55 degrees. Here is our x at 4, and our z is 5. So the question here is, are there different places where this 5 could land and hit this leg over here? Well, certainly we can see if we just trace this thing down, yes, certainly there's going to be a place in which this actually touches this leg. And because it's longer than this, there's no way that it could come around this way and still touch either. So really is only one triangle that could be formed from this. Again, we could do the law of sines. And after having gotten that answer of 0.6553, again, we can take arc sine of this, like sine to the -1, and notice that this is in between -1 and 1, so we're going to get an answer. And it's 41 degrees, or it could be 139 degrees. But again, we know that this angle measurement is not possible. Why? Because if you added this to the first angle measurement of 55, if you add that together, you already get more than 180 degrees. And remember, a triangle has 3 angles. So there's even another angle to be added, but we're already over 180 degrees. So there's no way that 139 is a possible degree measurement. So we know that it has to be 41 and only 41. What about in part C here? It says EFG, triangle EFG, where F is 5, G is 2.5, and G is 30 degrees. Okay, so we do have an acute angle here of 30 degrees. We have an F of 5. We have a G of 2.5. Now, in this case, we do need to figure out, because the G is smaller than F, we need to figure out if that is larger than H or not, or what it is in reference to H. So we need to find what H is. And the way we find out H, remember that we make a dotted line down, and we treat this then like a right triangle. Well, with right triangles, we know that we can just make use of sine here, right? If we take the sine of a number times the sine of that degree, we can get the opposite side. So in this case, so it's F sine G, which is just 5 times the sine of 30, and we get 2.5. So notice this, the height is 2.5. We're being told that the G leg is 2.5. So in other words, this leg equals the height. And if that's the case, we just have the right triangle. Okay, so for example 4 in the book now, we get to solve for an ambiguous case. So in this case, we have the triangle RST, and it's asking us to solve the triangle if R equals 3, S equals 5, and angle R is 26 degrees. So again, we can kind of sketch a little bit of a drawing here and get R angle of 26. We have our S of 5 inches, and the R, little r, the side that's opposite that angle, is 3. Remember, we need to, in this case, because it's an acute angle with the adjacent side being longer than the opposite side, we have to then figure out what this H value is, which again is just going to be sine of 26 times this 5 inches, which becomes 2.192. So note in this case that the height here is 2.192, which is smaller than the R, which is the R is smaller than the S. So notice here R is in between S and H. This is the case in which we can get 2 different triangles. And let's now just solve for that. We can use the sine of S over S equals sine R over R and get these values. We can then multiply this 5 up, and we get to the sine of S equals 0.7306. Remember, this is a number between -1 and 1, so we will get a value if we take the arc sine of this number, and we get 46.9. Remember, I told you this is a case in which we have 2 potential triangles. So we have to figure out what's the other triangle that can be formed from this. Well, it happens to be, if you remember from doing our radian unit circle, that all we have to do is take this 46.9, and remember, for sine, it would be this triangle or this triangle over here. So in either case, this angle is the same as this angle. So in order to know what that angle is from here, we subtract this angle from 180. So you take 46.9, subtract it from 180, and you get 133.1. So there's 2 triangles that are possible. One with an angle measurement of this, and the other with the angle measurement of that. So now in order to solve for both of those cases, we need to solve the triangle both ways. We need to solve if the angle measurement is 46.9. We also have to solve if the angle measurement is 133.1. Remember, we can solve for the other angle we don't know by just subtracting 180 from subtracting that 46.7 and the original 26 degrees from 180, and we get 107.1. We can then use the law of sines here. T over sine of t equals 3 over the sine of 26. We are going to just multiply this up above. So t equals, when you do that calculation on your calculator, 6.5 inches. In the second case over here, we again take 180 minus 26 minus 133, and notice that we get 20.9. Again, you would know if we were wrong in when I said earlier about there being 2 triangles, because if you did the subtraction again, you would get like a negative number or something of that nature. And if you did, then you'd know that this whole thing doesn't work at all. But in this case, we get a positive number, which means that the third angle is 20.9 in this case. And then again, we can just set up our law of sines, a little problem here, and get a t equal to 2.4 inches. So in both these cases, we could kind of then sketch little drawings of what this would look like. But notice here, in both these cases, we have these sides being 5 and 3. We have this 26-degree angle measurement. But notice that this triangle works either way because of this very unique case where this side length is longer than the height, longer than this height, longer than this height as well. But it's shorter than the adjacent side to that, to this angle R. Okay, exercise 21 in your book is another maybe good example that we could do quickly. Go to exercise 21 on page 274. There you'll see it says, find both solutions for each side-side angle case, round answers to the nearest tenth. So here we have an angle of 17, a side A of being 3, and B being 6. So we can just set up our law of sines here. And upon doing the law of sines, we get to this answer of 35.78 degrees. And then from that, we can also recognize that this would be the second angle that could be potentially possible from that measurement. So again, let's set up the two cases and see what happens. So if we have a B of 35.78, we subtract all that from 180, and we get this for the other measurement of the other angle. We can set up for C and get 8.2. We can then do the same thing over here for our second case. We take 180 minus 17 minus 144. Notice that we get an angle measurement that still is a positive number, so that triangle does exist. We can set up our law of sines and get an answer of 3.3. So notice you don't even have to necessarily go through just the rational logic of whether or not you have two different cases. You can actually just plug them in and see if you get answers. If you get answers, then you have two cases possible. So these are just kind of those two cases being shown to you. So at this point, you might be asking, well, what about triangles, though? I know you must be asking this question, right? What about a triangle when you have a side angle side situation or side side side? So in other words, what if I give you a triangle and I give you the length of this side, the length of this side, and the angle in between them? Or what about if I give you a triangle where I just give you the lengths of three sides? Can we solve those triangles? And the answer is yes, but you can't do it with just the law of sines. You need another law, the law of cosines, which we will look at in our next lesson together. So for your homework, what I want you to do is, again, watch this video a couple times if you need to. Read over 5.6. You need to complete pages on pages 273 to 275. I want you to do numbers 2 through 24 and then 44 through 52, the evens on all of those sign problems. Remember, these are going to be the new things. These last ones are going to be cumulative review problems. Please don't skip those. They are good reviews for you to go over and make sure that you're not losing sight of other things we've already learned, especially with a semester final coming up and not that long from now. It's good to be reviewing over that stuff as we go along. All right, so I know this is a lot of stuff, but just do your best, work through these problems. If you have any questions, let me know. Otherwise, God bless you guys. Hope you're doing well. I'll see you tomorrow or the next day to look at the law of cosines together.